We're now going to continue our discussion of limits at infinity by considering this theorem and some examples. So if we have a number r that is positive and rational, and you can see that number r is the power on a variable x in a denominator, 1 over x to the power of r, then the limit as we approach infinity or the limit as we approach negative infinity will give us 0 either way. Considering some examples might help with this. For example, just the most basic function 1 over x. Hopefully we all know what that graph looks like. And we could also consider 1 over x squared as another example. Those both have a horizontal asymptote at 0, whether we are approaching it from positive infinity or from negative infinity. That's basically what is going on with this theorem. We only looked at the two examples of 1 over x and 1 over x squared, so it's not a proof, but it illustrates what is happening here. A very informal way to think about this is that if we have 1 over infinity, considering direct substitution, which we're not really allowed to use with infinity, because infinity is the idea of a really big number. It's not actually a number. But you can think of this as 1 over something really, really big, which overall is approaching something really, really small, 0. It also works in the negative infinity case as well. This is kind of in parallel to what we've learned in the past, where if we had 1 over a really, really small number, then overall we were getting really, really big, approaching infinity. So we kind of thought of it as this, even though that's not really what was happening. We weren't really dividing by 0. We were approaching 0 in those denominators, causing those limits to get really, really big. So that was kind of our informal way of thinking about infinite limits. This can be an informal way of thinking about limits at infinity. All right, we are going to use our new theorem to help us evaluate this limit as x approaches infinity of sine of x divided by x. Well, if we try direct substitution, that doesn't make a whole lot of sense. First of all, dividing by infinity, well, that kind of goes along with our idea from earlier, considering this theorem where we were thinking about, okay, if the denominator gets very, very large, overall the entire fraction is approaching a very, very small number. But what is going on with sine of infinity on top? We can't just say that equals to 1. So direct substitution isn't going to work. But you might recall a theorem we have used in the past when working with trig functions. This would be the squeeze theorem. So we know that sine gets squeezed between the values of 1 and negative 1. Therefore, if we divide all parts of that inequality by x, then we have our function sine of x divided by x there in the middle. And we have two outer functions, and we can evaluate the limits of those two outer functions. So if I do that, limit as x approaches infinity, I'll start with the function on the left, negative 1 over x. Well, that is going to be 0. And if we look at the limit as x approaches infinity of 1 over x, that also equals 0 by our theorem above. Therefore, by the squeeze theorem, we can say that the limit as x approaches infinity of sine of x divided by x also equals 0. All right, moving on to another example. This time it's algebraic. We have a rational expression here. And remember, our theorem told us that we basically wanted all of our x variables to be in denominators. We have them in both numerators and denominators here. So the way for us to resolve that and evaluate this algebraically is to divide both the numerator and the denominator by the highest power of x from the denominator of the entire function. And that'll ensure that everything ends up looking like this form that we had in our earlier theorem. So we do that. Remember, this is still a limit. We need to continue writing that limit expression until we actually evaluate that limit. So I end up with, well, no fraction there, just 5 minus, basically I'm distributing that division is what I'm doing here, x divided by x squared, that's 1 over x, and then 1 divided by x squared is 1 over x squared. Same thing in that denominator, 2x squared divided by x squared is just 2. 4x divided by x squared, we end up with 4 over x, and then minus 3 over x squared. Now remember our earlier theorem, we had 1s in all of our numerators there, but if we have a different number, that's okay. For example, like here, if I take that limit, it's basically 3 times 1 over x squared. If this portion approaches 0 and I multiply it by 3, this entire expression is still approaching 0 overall. So what that means is as I go to evaluate this limit, the 5 has no x's, so it stays. 1 over x approaches 0. 1 over x squared approaches 0. 2 stays. 4 times 1 over x approaches 0. And then the 3 divided by x squared also approaches 0. So overall, my limit here is equal to 5/2. Let's try another similar example. Again, here we have x's in both the numerator and denominator, so to set this up properly, we look for our highest power of x from the denominator and divide by that, so in this case x cubed. Continuing to write our limit, this time we are approaching negative infinity. Simplifying, we get 1 over x cubed minus 1 over x divided by 1 minus 1 over x squared plus 1 over x cubed. And remember, everything that's a little mini fraction with x's in the denominator is going to approach 0 for that limit. So ultimately I get 0 divided by 1 here, which is just 0. All right, this next example wants us to describe the end behavior of the given function. So end behavior includes checking both the limits at positive and negative infinity. We need to check both of them. Even though they are often the same, we do want to make sure we check both. So our trick is to divide by the highest power from the denominator. Even if you know some other tricks for evaluating these limits, say you have seen some other rules from previous calculus courses, or maybe you know that limits at infinities correspond to horizontal asymptotes. Even if you know some of those other tricks, I still want you to show this algebraic work here. It's very important that you show your work. So here I end up with 3 times a really, really big number plus 4, all divided by 1 plus 0. So ultimately this is approaching infinity. And then remember, we also have to check the limit as we approach negative infinity of our same function, which we simplify in the same way, rewriting as this expression when we divide everything by x. And this time we get 3 times a really, really big negative number plus 4 over 1 plus 0. So this time we're approaching negative infinity. So what this means in terms of end behavior is as x approaches positive infinity, our function approaches positive infinity. And as x approaches negative infinity, our function approaches negative infinity. So visually, that looks something like this. We don't really know what's going on in the middle of the function, but overall this would be the end behavior of each side of the graph. No horizontal asymptotes here, but we're still describing the end behavior. Really quick here, I want to talk about a mistake that I sometimes see. Sometimes students forget when evaluating the limit that we want to take the highest power of x from the denominator, and instead they just divide by the highest power of x overall. So let's see what happens if we do that. If I divide everything by x squared here, because it is the highest power of x that I see, well, I still get a true statement if I was to rewrite this, because these are equivalent algebraically. But now as I go to evaluate the limit, I get 3 plus 0 divided by 0 plus 0, and I get 3 over 0. And that might lead you to accidentally say the limit does not exist. But then we have to remember that it's not that I'm dividing by 0, it's that my denominator is approaching a really, really, really small number. So if you keep that in mind, that this is just 3 divided by something really, really small, in fact, a positive really, really small number, not a negative really, really small number, then you can reason out that this is approaching positive infinity. Now, however, for the negative infinity limit, you'd have to remember that this is approaching a really negative small number, and that can sometimes lead you to accidentally forgetting the sign, or maybe assuming something is incorrect here. So just to avoid any of this, even though you could just still do it correctly here, it's a little more complicated, it's a little longer, but there's more chance for making mistakes. So just to avoid any of that, we remember to always divide by the highest power of x from the denominator to make the problem as easy as possible to do algebraically. All right, here's another end behavior problem. So again, we need to evaluate the limit from positive infinity first, and then from negative infinity, or we could really do them in either order, as long as we check both of them. The difference here from other problems we've seen is that we have that square root in the numerator. So we still want to use our trick of dividing by the highest power from the denominator, which divides in just fine in the denominator, because what I'm really doing here, again, is doing 3x divided by x minus 5 over x, which is why we get that 3 minus 5 over x there. But here in the numerator, you're not allowed to divide into a square root if this is not also under that same square root. So what I need to do is rewrite that x as something equivalent. Let's say the square root of x squared, because that simplifies to x. And now I have one big happy radical, and I can move them all under that same radical and then simplify as needed, leaving me still with a square root in my numerator there, but I have 2 plus 1 over x. So now that gives me something I can evaluate for my limit. So I get the square root of 2, the 1 over x goes to 0, and then 3 minus 5 over x goes to 0. So I get the square root of 2 over 3 here for that first limit. And remember, we're discussing end behavior. So if I want to, I can now say, as x approaches infinity, my function is approaching the square root of 2 over 3, which we know corresponds to a horizontal asymptote. So I can add that note, horizontal asymptote at y equals square root of 2 over 3. But remember, we still need to check the limit at negative infinity. All right, now evaluating the limit for negative infinity. Same algebraic trick, divide by the highest power from the denominator, which remember earlier, we treated that x as the square root of x squared. So we're going to do that same thing here. Instead of writing it as x, we are going to divide by the square root of x squared. However, I wasn't 100% correct earlier when I said that the square root of x squared simplifies as x. Because really, if x is a negative number, let's say I was looking at the square root of negative 5 squared, for example, that doesn't equal negative 5. What that equals, if I square the inside first, positive 25, the square root of which is positive 5. So that was just a quick example with a value to try to illustrate that realistically, the square root of x squared needs to equal the absolute value of x. That way we're not accidentally misinterpreting something with a negative sign. So building off of this fact, if I am trying to divide by the square root of x squared here, which simplifies as the absolute value of x, I need to consider how this absolute value function works. So the absolute value function can be thought of as a piecewise function, which equals x if x is a positive number or 0, but it equals the opposite of x if x is a negative number. Let's come back to that example of the square root of negative 5 squared. We saw that ultimately that simplified to positive 5. Which if I think of it in terms of this piecewise function, I could have simplified this as negative of the x value we're given, negative 5 in this case, which simplifies to positive 5. It's not the way we normally think about it, but we need to consider this extra negative sign here, the thing that makes it the opposite. Instead of negative, it's now positive, opposite sign. We need to consider that because of what's going on here. These aren't truly equivalent. Because I am approaching negative infinity, I'm in this case where my x's are less than 0. I have negative x values in this limit. So that means that this x and this square root of x squared are not actually the same thing, because this square root of x squared simplifies to the absolute value of x, which in the case we're in is the same as negative x. And let me clear some highlighted parts here. All right, so since the square root of x squared is equivalent to negative x in this case, because I am in this negative case for my negative infinity limit, and I need to make sure that when I divide, I'm dividing my numerator and denominator by exactly the same thing, I need to throw in an extra negative sign to compensate for that. All right, let's summarize. So I'm dividing by the highest power of x from my denominator, which in my numerator I treat as the square root of x squared. But because we are approaching negative infinity and this square root behaves as an absolute value when it simplifies, I need to throw on an extra negative sign, either in the numerator or in the denominator. Pick either one. And I do that to make sure that these are actually equivalent expressions, and I'm dividing the numerator and the denominator by the same thing. So let's go ahead and do that division now. So I have the extra negative sign. Otherwise, things simplify exactly the same way we saw above. And I end up with negative square root of 2 over 3. So we got the same value, but one is positive and one is negative. So now I can say as x approaches infinity, our function approaches negative square root of 2 over 3, which corresponds to a horizontal asymptote at y equals negative square root of 2 over 3. We can take a look at a graph of this to verify it if we don't believe what's going on. So here's our graph on Desmos, so you can see it written here. And if we minimize that, you can see that here towards the left, as we approach negative infinity, it seems like we have a negative horizontal asymptote, versus here on the right, we have a positive horizontal asymptote. And if I zoomed out and clicked on some points, I could maybe do some calculations and verify that those are approaching those square root of 2 over 3 values that we found. But I really wanted to illustrate the fact that some functions do have 2 different horizontal asymptotes. And algebraically, the reason we were able to correctly calculate that is because we thought through the process, making sure that that negative sign right here got accounted for. All right, looking at another example of a trig function, we're going to evaluate the limits at positive and negative infinity for the inverse tangent function. Remember, this is not a power of -1. That represents that this is the inverse function. You could also write it as arctan if you prefer. So let's start with the limit as x approaches positive infinity of our tangent inverse function. And really, there's no algebraic way to simplify this. You just need to remember your information about the tangent function. I like to do this by thinking about the graph of the function. So let's consider the regular tangent function. So this isn't the inverse tangent function. I'm starting with regular tangent because most people remember that one a little easier. And if we just consider the one period from -π/2 to +π/2, you might recall that it's undefined at those values because tangent is sine over cosine, and it's π/2 and -π/2 that make cosine equal 0. So we have asymptotes there. Now, if you take a look at the inverse, inverses reflect the input and the output. So if I was to graph the tangent inverse function, that reflects this graph. So the tangent inverse graph looks like this. And now instead of our vertical asymptotes being at π/2 and -π/2, those are horizontal asymptotes at π/2 and -π/2. Now there's other ways to consider this, but as I said, I like thinking about the graph. And it's that graph now that I can look at and say, oh, as we approach positive infinity, I'm approaching that horizontal asymptote at π/2. So there's my answer. And if I evaluate the limit as I approach negative infinity, well, that is the portion of my inverse graph that is approaching the horizontal asymptote at -π/2. Now, just a reminder here, earlier I mentioned tangent is sine over cosine. Remember, this is the inverse function, tangent inverse, arctangent, so it is not the reciprocal. Do not be tempted to just flip it and then try and consider cosine over sine. That's absolutely incorrect. I only mention that because I've seen students do it before, so I want to make sure you avoid that mistake. Some students prefer to solve this by considering the unit circle rather than the graph. So there's a couple ways to consider this. I like the graphs, so hopefully that is helpful for you as well here. Another way to consider this is, remember, for inverse functions, you're looking for angles. So you could also ask yourself the question, what angle makes tangent approach infinity? Or, since I've circled the most closest expression, this would be negative infinity. And then you could maybe consider, all right, sine over cosine, what's making that approach those infinity values, and use the unit circle, or maybe even use this original graph that we sketched here rather than the inverse graph below. All right, back to another algebraic example. This looks pretty straightforward. Evaluate the limit as we approach infinity of x squared minus x. Now, remember, direct substitution isn't something we really should do because infinity is not a number, but it's a nice way to just kind of mentally consider what's going on. So I have something really, really big, squaring it, still really, really big, minus another really, really big number. Infinity minus infinity. Well, that doesn't necessarily equal 0 because there are some infinities that are bigger than other infinities. Remember, infinity is not a number. This is not the same as just saying like 10 minus 10 is 0 because infinity is not a number. It doesn't work that way. So we don't really know what's going on here. This idea of infinity minus infinity, that's what we call an indeterminate form. So we're going to have to find some other way of working through this problem. Well, let's look at the expression we were given. Maybe there's something we can do to rewrite that. They both have an x, so I'm going to go ahead and factor an x out of this and write it as x times x minus 1. Now let's consider what would happen if we tried substituting a really, really big number. So I've got my x is infinity, and then the second parentheses, x minus 1. Infinity minus 1 is still a really, really big number. It's still infinite. And then if you consider infinity times infinity, well, infinity multiplied by infinity, a big number times another big number, is still a really, really big number. So our answer here is indeed infinity. And if you wanted to, you could just think about this function, if you don't believe it, well, that's a parabola. It's quadratic. We have an x squared as our highest power. So it should make sense that the end behavior is pointing upwards there, and we should get infinity as our answer if you think about the corresponding graph. That would not be the way of solving this algebraically and actually showing your work for evaluating the limit, but it's something you can think through to make yourself believe that you've done the work correctly. Let's do one last example, kind of similar to this. Let's evaluate the limit as x approaches infinity of the square root of x squared plus 1 minus x. So if we were to use our idea of direct substitution, plugging infinity in, we get infinity squared plus 1 is still infinite. Take the square root of something infinite, it's still infinite, minus something that's infinite. So we said if we have infinity minus infinity, that's indeterminate. We don't actually know what that equals. We can't assume it's 0. We can't assume it's 2. We can't assume it's infinity. We don't know what's happening. So we need to find some way to rewrite this expression. So in the past, anytime we had square roots and needed to rewrite it, we used conjugates. And the key of conjugates is that you could multiply the numerator and the denominator by the conjugate and end up with something equivalent. Well, we don't have a denominator, but of course we can write anything over 1 and it becomes a nice fraction. So we're going to do that, and then we're going to multiply both the numerator and the denominator by that conjugate expression. Simplifying that, our square root gets to go away, minus x squared, all over that conjugate expression. In the numerator, the x squareds are now gone. So now we have done all of the algebra to simplify, which is why I'm still rewriting the limit. I have not evaluated that limit yet. Now I will go ahead and do that. And notice that all of our x's are in the denominator here. So I could just say, well, this is infinite plus something infinite. Notice this time we have that plus sign there. So it's okay to add two really, really large expressions, giving us a really, really large number in the denominator. So overall, we're approaching a really, really small number, 0. So that's going to be our answer for this problem.